That was good, right? All right, so today we're going to continue with algorithms and algorithm analysis, of course. Remember our motivation here is that we want to analyze algorithms with respect to their performance, and as a 5-step process, you identify the input size, the elementary operation to capture the notion of work, and then you come up with a characterization of that algorithm with a function that tells you that on an input size of n, it takes this many elementary operation computations. And then as part 5 here, or as step 5, you can simplify that characterization down into one characterization using big O analysis. Okay. Now, that's where asymptotics comes in. All right. So again, our motivation here is that we want to characterize an algorithm's efficiency or performance with respect to its input size, n. Right. And we're more interested. We're interested in its performance as n grows. All right. In other words, as the input sizes get larger and larger and larger. We're not necessarily concerned with small input sizes. If you remember back to when we began this whole module, I gave you a demonstration on a linked list. That doing something on a linked list was inefficient the way that we were doing it, and then we switched it to a way that we can do it efficiently. But when even when we were doing it inefficiently, on small input sizes like a linked list of size 10 or 20 or 100 even, it really didn't matter because it went by in a blink of an eye. But when we started increasing that to 1 million, 10 million, 1 billion, right? Now you're talking about a difference of 20 years or something was our estimate, right? So we're really concerned in the aggregate. As the input size grows, how bad is it actually? For larger and larger inputs, the growth rate of that function, we want to characterize that growth rate. What order can we give it, basically? And again, one of our other motivations is we want to be able to ignore constants. Right? We want to ignore lower order terms. Right? And we don't want to have to worry about those things. Because again, this constant sitting out front changes if you move it to a faster hardware. The lower order terms, who cares about those when you've got this degree 3 polynomial over here? Who cares about this constant term over here or this linear term over here? This is what really matters. That's what's really going to grow as n tends towards infinity. All right, and the tool we use is big O analysis. All right? And so again, as a review, big O is literally O, it's the Greek letter omicron, but there is no difference. So we just say big O. All right. So there are definition. So there are. I mean, this comes from old school calculus, 100 years before the first actual electronic computer was invented. These asymptotic ideas were from calculus. And so they've been around a long time. It's only more recent that computer scientists have said, oh, okay, well, we'll use that as a tool for analysis of the algorithms. Oh, yeah, that sounds like a reasonable tool to use. So this stuff is actually quite old, and it deals with just functions. And in fact, there are a whole collection of asymptotics. There's not just big O omicron. There's little o. There is theta, there is omega and little omega, and a bunch of other things that you can use to characterize the growth rate of functions in calculus. Big O is what we're going to focus on, though. We're going to winnow it down and focus only on this one thing. So here's my full definition. Here's the full mathematical definition. Let f and g be functions, right? And note here I'm using them as functions on n because n, again, is our input size. I don't want these to be continuous functions. I don't want them to be on x and y because that tells me that you can have negative input values. You can have input values of fractionals like an input size of 3.5, right? That doesn't make any sense. We say that f of n is big O of g of n if there is a positive constant c and an integer n naught such that we can come up with this inequality. f of n is bounded above by g of n multiplied by some constant c of n, or c, sorry, after a certain point. All right? So in other words, for all n greater than or equal to n naught. Now, to understand this, let's just draw a picture. Right? Give me two. I'm gonna write out two functions here on Wolfram Alpha and tell Wolfram Alpha to plot them. Right? So plot, I don't know, 175 or n squared plus 4n and then separately, this is a separate function now, n cubed. Okay, and I'll go ahead and plot it for n running from 0 up to 100. There, nice visualization. I'll even zoom in on it here. So remember, don't lose the forest for the trees now. What is this actually plotting? Those two functions, right? This function, 175n squared plus n, is characterizing some algorithm. N cubed is characterizing another different algorithm. So we're comparing two algorithms here, and their performance as n tends towards infinity. This is basically, I just made these functions up, but you saw an actual function last week, right, I think, where I showed you the experimentation that I ran at some point, and then I did a quadratic interpolation to fit a line to it, right? Well, these are interpolated functions, if you want to think of it that way. What is the x-axis capturing again? The size of the input, right? What is the y-axis capturing? Cost, some resource. It could be time, it could be power consumption, it could be memory, et cetera, et cetera. It could be any dozens of things. We're taking it as more of an abstract idea. So, with that in mind, as the input size grows, your cost increases, your time increases, or your memory increases. So, which algorithm would be better just looking at this picture? Is higher better or is lower better? All right, based on this picture alone, right, in general, if I've got two functions, the higher one is using, the interpretation of this is that the higher one is using more resources, right? So the blue one, which is the n squared one, is telling you that it's using more resources. But it's only telling you that because I only looked at it for linked lists, say, of size 0 through 100, right? What if I zoomed out a little bit more and mapped this from 100 or 0 to 200? What would it look like then? Right? At some point, this magic crossover point, right? Now the red function becomes more expensive because it's on top of the blue function. Big O analysis characterizes functions like this. That, yeah, okay, this function might be less expensive for small input sizes, but I don't really care about that because they're all the same. At some point, this function will always be greater than this function, right? So that's what the definition is saying. That after some point, n naught, right? This over here, the interpretation of this crossover point right here, that's my n naught. At some point, this function will always be greater, g of n will always be greater than f of n. Right? Now, why do we throw the c in here? What if you take a function, now here I'm going to just map one of these functions. I'll go ahead and take this function this way. And what happens when you multiply a function by a constant? It's not going to be able to understand this because c is not known, but what if c were 1? Right? I get the parabola, you know, like you'd expect. What if I multiply this by 10? Is it going to change it from a parabola into something that's not a parabola? Nope. The growth rate, in fact, over here is going to stay the same, basically. In fact, the picture is not going to look any different, only the scale has changed. Right? But what have I essentially done by multiplying it by a value? If I've got a curve here and I multiply it by 2, I'm just making it a little bit steeper, right? A little bit steeper, a little bit steeper, a little bit steeper by multiplying by a constant. But the growth rate is unchanged. It's still a quadratic, or it's still a linear, or it's still a cubic function. Right? So what is this c doing here? It's just saying that, well, if you want to, you can go ahead and make an adjustment, and you can make it a little bit steeper if you want to. That changes the crossover point. Right? It could it could move the crossover point this way, or it could move it this way if you multiply by something that is less than 1, etc. That's all that it's doing there. It's saying that after some point, if you want to go ahead and change this, this curvature a little bit, it doesn't matter because it only changes the crossover point. After some point, this function is always going to stay on top of that function. Therefore, this function is big O of this function. And take away the intuition here of the less than or equal to. The growth rate of f is at most the growth rate of g, or the growth rate of g is at least as big as the growth rate of f. Right? It sets up a way to compare two functions and their relative growth rates. All right? Ultimately, it characterizes a function's order of growth as n tends towards infinity. Right? It basically says that g of n has a growth rate at least as big as f of n. Or another way of thinking about this is that f of n, the growth rate of f of n is bounded by the growth rate of g of n. Right? Or put another way, plain old English, is that asymptotically, g of n is at least as big as f of n. And here I'm not saying bigger. Right? If I said bigger, that inequality would be a strict inequality, strictly less than. Right? Something like that. I mean, that would be the interpretation. You'd have to have a different definition that relied on calculus and limits and stuff like that. But that's the idea. Okay? Why is this nice? It captures everything that we wanted. It allows you to ignore lower order terms. Why? Well, because you can bound them by the highest order term. Right? If there's a lower order term over here in g of n, throw it over onto the other side, right? Basically algebraically. It allows you to ignore constants. Why? Just go ahead and collect all the constants you want and throw it in, and it gives you a different c. Who cares? It allows you to focus on the most significant term in a function, the highest growing term in the function. Some miscellaneous here, especially if you've taken 235 or 235h maybe currently, if you've gotten to that point. We usually write f of n is equal to O of g of n. Right? When we say that f of n is big O of g. Right? That's an abuse of notation. It's still okay though, because it's ubiquitous, it's normal, it's been normalized, I guess. But the real way of writing this is to use set notation. F of n is in the class of functions bounded by g of n. Right? So again, we don't assume 235 material here, but if you're familiar with it, then that's another way of writing it. Okay? So don't get confused when some authors use equals. That's technically not correct, right? And other authors use the proper set notation there. Right? Another thing to note is that it is not a tight definition. Again, it is less than or equal to. It is only establishing a relative order of growth, that this thing is at least this thing over here, or this thing is bounded by this thing over here. It is not tight at all. What I mean by that is, if I wrote down 3n plus 3, that's clearly a linear function. And so the conclusion that you're going to have is that it's big O of n. It is bounded by any other linear function. It is also true, however, that it's bounded by a quadratic, right? It's just loose, right? You can just make it bigger and bigger and bigger and bigger, less than or equal to, right? If I said that 50 is less than or equal to 50, that's true. 50 is less than or equal to 100, right? That's still true. Just making it bigger, the inequality, who cares? You can make it as big as you want. Right? It's also true, of course, you can keep going up if you want to. You can say it's bounded by an exponential. Right? That's why it's not a loose, or that's why it is a loose bound. If you want a tight bound, you're shopping for a different asymptotic called theta, right? Theta shows a bound from below and a bound from above. Basically, it allows you to define three functions now, or not three functions, but if you've got a function here and you can bound it above and you can bound it below, and basically you've trapped that function inside of two other functions, the growth rate that is, then you've shown that all three of these functions have the same order of growth. Yeah?
Would you say that 3n plus 3 is equal to theta of n squared? Because when n is 0, the thing on the left is going to be 3.
Remember, we're not looking at any particular point, right? We're looking at the growth rate, right? It is definitely, you're right, it's not the case that they're equal when at 0, right? What are the, here, let's go ahead and map those. Plot n and 3n plus 3. N equals 0, just up to 5, right? Oh, you wanted n squared? Sorry, n squared. There we go. There. So there's the crossover point, right? We don't care about 0. We don't care about small input size. Input sizes of 0, 1, 2, 3. Clearly, the red one is doing worse than the blue one because it's taking more resources. But after you get to this point, clearly this blows up, right? And big O analysis allows you to quantify that. I don't care about I don't even care about inputs of size 0 up to 1 billion, right? If the crossover point is at 50 trillion, I care about everything after that point, right? At least asymptotically, at least theoretically. Okay. All right. So how do we go about proving these things, right? The question is, that given these two functions, f of n and g of n, how do you prove that f of n is g of n? First of all, you've got to come up with an intuition saying that, well, that one looks like it has a higher order of growth. And that one looks like it has a lower order of growth. So I set up my, my supposition that f of n is g of n. If they're opposite, well, just go ahead and swap them, right? Once you've done that, though, there are two techniques that I'm going to show you. There's a third technique that we're not going to go over, the limit method. And I think I briefly discussed that last week, where if you take the ratio of f by g and you take the limit as n tends towards infinity, if this one on the bottom is growing much faster than the one on top, right, it's going to converge down to 0. If this one on top is growing much faster than the one on bottom, it's obviously going to diverge. If it converges to a constant, that means that they have basically the same order of growth. Right? That's calculus. That's and certainly, if it were my choice and I were given the problem and I had to show big O analysis, I would jump right to the limit method, because you have a whole calculus toolbox that you can bring to bear: L'Hopital's, known limits, first derivative, second derivative, etc. You can use all of that stuff to come up with a very easy limit-based proof. But we're not assuming calculus here, so I'm going to show you algebraic approaches instead. Approach A is the less useful approach in my opinion, so we'll do it first and see why it's less useful. You find the crossover point. Crossover point, where one function becomes larger than the other for all values greater than the point, the crossover point. Right? Essentially, what this means algebraically is that you fix C to be 1 and find n not. Right? Remember, in the definition up here that I'll scroll back up to, we have two variables here that we have to find. F and G are given to us, and we have to find a C and an n naught such that this inequality holds for all n greater than or equal to n naught. So the idea here is, since you have two variables, fix one of them and find the other. Because if this is true, actually, then you have an infinite number of pairs for which this definition is satisfied. Right? And to find one, it suffices to find one. All you need to do is set one of them and then find its companion, or one of its companions, because again, there are an infinite number of them. It doesn't matter which one you find as long as your proof demonstrates that C and N naught are true, or true for that one, right? So this is the idea. Now let me go back to my old, there we go. And back one more. Back one more. Back, there we go. That's what I wanted, all right? So visually, what you're trying to do is you're trying to find this point for these particular inputs, okay? We've got a quadratic form, we've got a quadratic function and a cubic function. How many times do you think that these functions actually intersect with each other? How many potential crossover points are there? Well, let's find out. Right? And for that, I'm going to have to bring this up. All right. So let's go over here. What were they again? 175 n squared plus 4n versus n cubed. Okay? I'm going to fix c to be 1, and I want to find that n naught. So let's go ahead and set up that inequality in the definition, and let's see what it looks like when I get rid of c. So 175 n squared plus 4n is less than or equal to c n cubed for all n greater than or equal to n naught. I need to find this n naught, but as a first step, I'm going to get rid of c. How am I going to get rid of c? By making it 1. Great. Now all I need to do is find an n naught for which this inequality is true. It's an inequality, and so I can set it to an equality to tell me when the thing on the right-hand side is equal to the thing on the left-hand side. Right? So let's go ahead and transfer it into an equality. At the same time, let me go ahead and make it a little bit more familiar to everybody by collecting everything onto one side. In other words, what I'm going to do is I'm going to take these two terms and move them over here. And what am I left with? N cubed minus 175 n squared minus 4n is equal to 0. And exactly, it's a polynomial, and so I need to solve for n. When is n, for what values of n does this equation get satisfied? Oh, okay, you immediately saw one. Why? I can factor out an n equals 0 immediately, right? What am I trying to do here, though? Before we get into that, you found one immediately. What did you find? What would you call that thing? It's a solution, and in the context of polynomials, they are useless. All right, well, let's take it one more step before we come back to that answer. And if I factor out an n, and n is equal to 0, then what am I left with? N squared minus 175, factor out an n minus 4 is equal to 0. I want to find the other two remaining, what do we call them things? Crossover points, or? So what? I want to solve for n here. What am I going to have to bring to bear here? It's a quadratic equation, so I need the quadratic formula. What does the quadratic formula give you at the end of the day? The roots. Good. I'm simply trying to find roots here. And by the way, if I had added something else here, could we have done your trick and factored out an n? Nope. That's why I manufactured this exactly how I wanted it to. Because does anybody know off the top of their head how to find the roots of a cubic equation? No? You'd have to look that up probably because I mean, there is a process. I think it's a couple of cases that you have to go through. Does anybody know how to find the roots of a quartic equation, or a degree 5 equation, or a degree 7 polynomial, or a degree 50 polynomial? Yeah, okay. Half the time, yeah, I forget it too, because I think I wrote it wrong this morning. But to find the other one, it's going to be negative b plus minus root b squared minus 4ac, that's the radical, all over 2a. Right? All I need to do is plug in a is 1, b is negative 175, c is negative 4. So help me remember that. Negative 175, so negate that, 175 plus minus 175, I'll just go ahead and immediately get rid of the negative because I'm going to square it. Minus 4a was 1, c was what? Negative 4, so plus 16, all over 2a was 1, so we've got this, whatever the heck that is. All right? I don't even like doing that stuff. Again, let's do Wolfram alpha. And what are the roots of that equation? Roots of n cubed, what was it? Minus 175, 175 n squared minus 4. Oh, 4n, sorry. A, just as you predicted, one of them was 0. What about this one? I'm going to open that up into a new tab because they only give you a symbolic representation by default. And here's the actual representation. If you go all the way back to this thing over here, that means that if I expand this out to say, let's go from negative 1 to positive 1, you'll see that it's this degree theory is going to have this two-dimensional saddle point, right? I don't even know if it's going to show up because it's so small, right? It's so small that it's negative 0.02. It intersects at 0.02, it intersects at 0, and then it intersects at this third one that we have yet to look at. Is this one relevant? No. Why? It's negative. Is there such thing as a negative input size? Nope. So we can throw that one out. We can throw out 0 too because we were looking at this and whatever the crossover point is, it's much larger than 0, right? There we go. Go up to 200 here. Right? There is a crossover point at 0, but this is the one that we're interested in. So this is the actual root. And of course, I was doing this all on my calculator or on a piece of paper or something, computing all these numbers by hand. 175.02. That's my crossover point technically, but is that my n naught? No, because can we have a fractionally sized input? No. But don't worry about it. You can always go bigger, right? Don't go less, because that's not where the crossover point is. Go after the crossover point at, say, 176. Right? So, after this has been, come on, don't go to sleep. Right? So, for c being 1 and n naught being, what did I say, 176? F of n is bounded by g of n. Right? In other words, i.e., f of n is less than or equal to c g of n for all n naught greater than or equal to 176. And then, of course, my c, I don't even need to retain that anymore. I'll go ahead and keep it here, c being 1. Right? Now, again, how jazzed would you be about finding all the roots of a 50-degree polynomial? Finding the roots of logarithms. Finding the roots of exponentials, right? I don't want to do that much work. So, approach B, right? Yeah, go ahead.
Is there any significance to the crossover point being just 1 greater than r?
Because it's integers, right? That's your that small value there is your crossover point, but that's not an integer. The definition of big O is There's a positive constant c and an integer n naught. I can't give you 175.03. That's not an integer.
No, I just.
But I can go one larger to get the next integer. Right?
Yeah, I just remembered our b value was -175.
It's just because that's no. It's quadratics and cubics. That's why. Right? It's just the quadratic. It's just the coefficient of the quadratic. I mean, it's because the b squared minus 4ac in the radical that this is going to dominate because it's so much larger because it's squared. And so when you take the square root, it's basically like canceling it out and getting b, yeah, which was the 175 in my equation. That's the only connection. Right? Okay. So approach B. Well, if the approach A was to fix C to be 1 and find n naught, the approach in approach B is to fix n naught and find your C. So fix n naught to be 0 and find a C such that the inequality is satisfied. Right? It doesn't have to be the tightest C. It doesn't have to be the smallest C. Right? It just has to be a C that works. And that's the beauty of this approach, is that it doesn't really require any thinking. All you have to do is start out with F and make it bigger and bigger and bigger until it looks like G. Right? So let's look and see what that looks like. Come on. All right. So here are my equations again. 175n squared minus 4n, or was it plus 4n? Okay, versus n cubed, right? We want to show that 175n squared minus 4n is less than or equal to some c times n cubed for all n greater than or equal to n naught, for some n naught. In other words, again, what I'm doing here is I'm going to fix this to be 0. And now all I need to do is find the c. Okay? This is what we want to show. I'm not there yet. I start on the left-hand side, and I will eventually derive the right-hand side. So let's start with the right-hand side here. 175n squared minus 4n is less than or equal to something bigger. Now, I could go crazy here. I could certainly say 1 million n to the 50. Right? You buy that, right? I just made it huge. But I've also gone, over jumped my target of n cubed, right? So let's not do that. I want to make it look like this thing over here. So how could I make this thing bigger so that it looks kind of like this? It might be a step-by-step process. So you observe that we could factor out an n from the last approach. What's to stop us from multiplying by an n? Doing just the opposite. Multiply by an n. Right? 175 n cubed minus 4n squared. Is that true? Yeah. For all n greater than or equal to 0. It's not necessarily true for negative n, right? In fact, I'm sure that no, you could come up with an example where it wouldn't be, right? Okay. The first term kind of looks like n cubed. The second doesn't, though. The beauty about this is that we don't have to make the entire thing bigger. We can make individual terms bigger as long as that inequality is satisfied. What I mean by that is this is 175 n cubed minus 4 n cubed. Right? Is it? I made this thing bigger. But I'm subtracting it, which makes the entire thing smaller. You have to be careful. Yeah, go ahead. All right. So, back it up here. How do I make that bigger? don't have it, yeah, I could say less than 4n squared plus 4n squared. Right? So if I've got negative coefficients, I can just add that thing back in, right? Now it's certainly true that this thing 0 is less than or equal to 4n squared for all n greater than or equal to 0, right? So by adding this one term over here, the inequality is still satisfied. Right? And these two will end up canceling out, and guess what? 175 n cubed. So what's my c? 175. What's my n naught? 0. That's what I started out with. Right? So those are two ways of showing a proof. Right? Hopefully you'll agree with me that this second way is way easier. It's just algebraic tricks. Right? Yeah, go ahead.
So 1 is 175 and 1 is 176.
That was just, yeah. What if I had made this plus? Then I won't. But what if I had made this plus? This trick would have still worked. It's just I get another number, right? C being 183 because it's my favorite number, greater than 175. It doesn't matter. Making it bigger doesn't matter as long as you don't make it too big, like 1 million n to the 50, right? Okay. I didn't open it here, but some people have been asking about assignment, the last assignment, which is actually assignment 8. Assignment 8 is a written assignment. It is traditionally required in this course, but because of the shortened 15-week period, as well as accommodations for student wellness, we've made it required, but not graded. Right? So take that as you will. No, you don't have to do it, but we strongly suggest that you do it. If you want to wait until after the semester is over and then do the work, the reason we say it's still required is because you're still expected to know this material for going on in the rest of the program. Right?
Are we learning these kind of things in the pre-sign 3?
It'll be assumed for the most part, yeah. That in 235 you should be covering this maybe, or was it cut? You have 3 weeks left. Are you covering the limit method?
Yeah.
You are? You are? Okay, you have. All right, good. Let's get some practice. Let's do the homework together here. All right? What about that first one? What about that first one? 3n versus n. All right, well, this A. I want to show that 3n is big O of n. I need to show that. What C? Yeah, or 4. Or anything greater than 3, ... Right? Choose your favorite number, 42, and that'll work. Right? That's not that big of a deal. Yeah, go ahead.
Would it be more valuable to express C as an inequality?
I mean, it's certainly going to be true, but that's not what the definition is. The definition fixes C, and then for all n greater than or equal to n naught. That's where the inequality comes in. So, but again, you're right in that, again, there are an infinite number of pairs that will work. So if you fix an n naught and a C, certainly if you have any larger C, that just means that you're moving the curve up and making it steeper. It doesn't change the fact that it's already crossed over. Right? So you could potentially have an equivalent definition here where you fix n naught, and then for all C greater than or equal to C n naught, you could redefine it, right? Let's go with this. How about this one right here? N squared plus 2n plus 1. And we want to show that that's big O of n squared. Yeah?
So n naught can be a fractional number, but C can be a fractional number? Like,
In our definition, yes. N has to be an integer, and C can be a fractional number, not negative.
yeah.
Because negative, all you're doing is shifting it down. Now, in the actual definition, like the calc definition, everything can be a real number. It doesn't matter. You can have monotone decreasing functions and also bound those. The application that we're using it for algorithm analysis is very special because you can't have fractional inputs. You can't have negative sized inputs. You will never have a function that arises, or you generally won't have a function that arises like sine of x in your analysis, right? That's not a monotone increasing function. You could have an algorithm that kind of has this behavior, but from a practical standpoint, what is it taking? It's taking at most this many resources, at least this many resources. When you look at worst case scenario, it's this thing right here. It's a constant, order 1, right? Because it doesn't matter what the input size is. As the input size grows, it's always bounded by 1 if it's sine, right? And so we can say that something is order 1. In other words, it's constant. It doesn't depend on the input size. It's just a formula evaluation or something, right? All right. In fact, yeah, let's take a detour here and let's mention those classes of functions. This is constant, right? We've already seen, say, order n, which is linear, right? We've seen bad algorithms that are also quadratic. We've also seen, say, from last semester, algorithms that have logarithmic behavior. I've probably only seen one. Do you remember what it's called? Binary search? That's all right. We'll look at it again by the end of the day, probably, right? Order logarithmic. Where does that lie in what we have so far? Is it better than constant? Nothing gets better than constant, right? You can have a 0 growth rate. Well, that's what constant is. If you take a constant function and you take the first derivative, what do you get? 0. It's a constant, it's a 0 growth rate. It's not growing at all, right? Is it worse than linear? No, logarithms are definitely smaller than polynomials, right? So it belongs right here. Right, this is logarithmic. There. You've also seen things that are order n log n. Quick sort and merge sort, which we'll revisit. Where does that lie here? Hint, I put white space in there for a reason. Right here in between these two. And this is, we do have a name for this. This is called quasi-linear. Almost linear, right? In fact, there are there's a big O version with a tilde above it that allows you to ignore logarithmic terms, and so this quasi-linear here is quasi-linear, and this special tilde above it just says ignore all those logarithmic terms. Why is it okay to ignore logarithmic terms? Because it's such a slow growing function, right? You have to get up to billions in order for it to go from like 7 to 8, right? What else do we have? If I went up to 3, it would be cubic. In fact, we can generalize all polynomials as n to the k. Right? Polynomial. And theoretical computer scientists love all polynomials. It doesn't matter if it's n to the 16th. We've shown a polynomial time deterministic running algorithm for this problem. Close the book, we're done. But we've seen from a practical standpoint, anything above this red line here is not practical, right? You can keep going though for super impractical things like order 2 to the n, order 3 to the n. And of course these are exponential, right? Not all exponentials are created equal. 2 to the n, 3 to the n is much faster growing than 2 to the n. Right? Question?
Why do you guys love n to the k polynomials?
because we just shown we've shown that it's in the complexity class P, and which is for theory purposes, that's efficient. It doesn't matter if it's n to the 1,000, right? Oh, okay, then it's P. We don't have to worry about it anymore because we're never going to program it. You can go even higher than exponential. What is that thing right there? That's factorial. That's super exponential. Right? What does that correspond to? In say 235. N factorial. No? What if I gave you A, B, C and told you to arrange these things? How many ways are there of arranging 3 of these things? You can go A, B, C. You could go A, C, B. B, A, C. B, C, A. These are all permutations. And C, B, A. Right? Permutations. And how many permutations were there when there were 3? 3 factorial, which is 6. In general, though, it's n factorial. So can you consider all permutations, say, of a deck of cards? A deck of cards, there's only 52 of them, right? That's small input size. 52 factorial. The exercise that I usually do in 235 is, think about this. Think about shuffling a deck of cards. Every single person on the planet, 5 billion of us, let's say, shuffling a deck of cards once per second. How long would it take us to get all possible permutations? It would take you till the heat death of the known universe and beyond, right? So, not, and say what?
Nothing.
Okay, all right, question?
So basically, I wanted to write an algorithm or create an array of all possible combinations that would be an n factorial.
Oh, you're saying combinations when combinations are different? If you mean permutations, it will not execute with you. Now, order 10 factorial, that's certainly doable. 12, 13, 14 factorial, you're getting to, now you jump up at some point and it ain't going to be in your lifetime. Right? In fact, if you do lab 12, which was cut for recursion, it's not factorial, but it is exponential. You get, what is it? I forget, Fibonacci sequence, but it grows exponentially. If you try to do the naive solution recursively, you can estimate it though. This will take me 52 years. This will take me 1,000 years. This will take me 1,000,000 years, right? And it grows like that, right? Exactly. Yeah, you're not going to get your homework done doing that. All right, so go back to this simple polynomial though. Right? I want to show that this is order n squared. Right? So n squared plus 2n plus 1. How do I make it bigger? I could multiply this one term by n. I could multiply this one term by n squared. Right? N squared plus 2n squared plus n squared. Right? And what's my justification here? It's because 2n is less than or equal to n squared for what n? Or sorry, I'm just making this term bigger here, right? So n is less than or equal to n squared for what n? Yeah, does it work for negative n? Nope. Yeah, I guess it does. Yeah, technically. 2, yeah. For all integers n, but there's got to be like, I don't think that the linear function is tangent with the parabola. Is it? There's got to be some little speck in there that is not true, but it's certainly true for all integers. And also, the third one is definitely true. 1 is less than or equal to n squared. Uh-oh, wait a second. Does that work for all n? For all n greater than or equal to 1. So here I'm going to have to adjust my and not. Right? And this thing can be simplified by collecting all the terms into 4n squared, right? Which looks like this up here. So for c being 4 and n not being 1, the inequality holds. More practice? What's another interesting one here? Here, e. N log 32, n, and n log n. We're asked to show log n, there we go. We're asked to show that this is big O of this. And it makes sense because we could kind of ignore this constant sitting here because that's the point of big O analysis. You can ignore constants. But if you were just to look at it, is it true that n log 32n is less than or equal to n log n? Ignore asymptotics for a second. Is that inequality true? No, it is not. Right? So we have to show our proof here. Let's go ahead and go with n log 32n is less than or equal to, well, before we make it less than or equal to, let's get it into another form here. That log 32n, how could I rewrite it? At this point, you need to start remembering your log identities. Right? Log of a times b is equal to log of a plus log of b. Right? So I can split the 32 and the n up into log 32 plus log of n. Now log of 32 is what? Don't pull out your calculators. Remember, we are self-respecting computer scientists. All of our bases are base 2. So 2 to the 5th gives me 32, right? So this is equal to n times 5. Oh, wait, 5? 4 would be 16. Yeah, I think I screwed it up. No, I got it right. No, I think I screwed it up in today's, or in this morning's section. I think I said 6. It doesn't matter, it's bigger. All right? So this is equal to n log n, which looks exactly like what we wanted, plus 5n, which is not what we wanted. But guess what? Now we can go into our little tricks and make it bigger. N log n plus 5n, and all I'm doing here is adding a log n. And is that true for all n greater than or equal to 0? Careful. Is log 0 defined? Nope. Log 1 is defined, so we're good there. Right? And that's equal to 6n log n. So for c being 6 and n not being 1, the inequality holds. You just have to be careful on your algebra and make sure that it's all valid. Right? What about this one right here? This is usually, it's just as simple as the other ones once you see the trick, or once you figure out the trick. N to the 2n versus 3 to the n. Right? Now if you just go along and you start to do what we did before of starting with the right hand side and making it bigger, right? You're tempted to try to combine these two terms into one by making the n bigger. Right? What's that going to end up being? Say what? 2 to the 2n, why? 2 to the n plus n, right? So 2n. And then what can you do with that 2? Four n, right? But guess what? You've jumped the shark. You've gone too big. All right, back it up. Man, I love iPads now. Right? Did not love the price that I paid, but believe me, I also paid the extra $300 for infinite screen replacements. So if you do get an iPad or something like that, get the insurance money. I think it's actually only good for 3 or 4 years on something, but hey, at the end of 3 years, you can go ahead and
Almost infinite, but not sure.
just a little smash. Just start being a little bit more careless. All right, that's too big. Let's not go too big.
Just get really mad at some things.
I want something that when I multiply it by 2 to the n gives me 3 to the n. What can I put in that something? Okay, 3 over 2, or another way of saying that is, I like decimals. I don't like 3. Yeah, you said 3 over 2, right? To the n. Right? That's certainly true, but also 1.5 to the n times 2 to the n. Right? Why? Because n is less than or equal to 1.5 to the n for all n greater than or equal to what? Now at this point you start trying things. 0, yeah, that works. 1, yeah, that works. 2, pull out a calculator at this point and start thinking about it. It's 2 and 2.25. 3, yeah, that works. 4, yeah, that works. I personally call this obvious land. Right? So now if you were doing a limit proof and you had something like this, the limit as n tends towards infinity of 1 over n, if you were in an analysis course or maybe a hardcore calc course, you would have to come up with the limit definition. You'd have to find an epsilon and a delta such that for any epsilon you can find a delta that it's arbitrarily close to 0. Right? I say that we're in obvious land at that point. That's going to be equal to 0. Likewise, in the algebra world, I'd say that this is obvious for all n great. Oops. For all n greater than or equal to, well, 0 will work. Right? Now, what is that equal to? 3 to the n. So for c being 1 and not being 0, you're good. Right? One last one, and we'll reassess the time here. That thing right there. Log of n squared. N squared is huge though, right? I'm on h now. Log of n squared, or n factorial, excuse me. N factorial is huge, right? But when you take the logarithm of something huge, logarithms are small, so it tends to kind of even out. Right? We want to show that this is big O of n log n. In other words, it's not that big. Right? Right? Ideas. Good. We could separate this out into what? Well, first of all, let me write down what n factorial actually is. N times n minus 1 times minus 2 times ... 3 times 2 times 1. Right? This thing is equal to this thing. Okay? Now, you said that you can separate that out using the same log identity that we did before. Log of a times b is equal to log of a plus log of b. All right? But before we do that, I'm going to make this a little bit bigger and use a different logarithm identity. That is a perfectly valid proof, right? And you just go down a different hallway to get to the same place, right?
Let's see where you do it and you're gonna do that in
Eventually, yes. N times n times n times ... n times n times n. What did I just do? I replaced each one of those terms with n. Why? Well, 1 is less than or equal to n for all n greater than or equal to 0. 2 is less than or equal to n, so I made this one bigger, I made this one bigger, I made this one bigger, I made this one bigger. This one just stayed the same. That's why it's less than or equal to. Okay? That's equal to, how many n's are here? n. So n times n times n times n times gives you n to the n. And now one more log identity. What can I do with that exponent? put it out front. Right? Log of a to the b is equal to b log a. Right? And that's what we are aiming for over here. Right? So what's my c? 1 for n greater than or equal to 0.
It wouldn't be 0.
Aha, good. Why?
Because 1 isn't less than 0 and 2 isn't less than 0.
Good. It wouldn't hold over here. So let's go ahead and move this up. But that does raise an interesting question. Going back to this over here. What is 0 factorial? 1. It has to be 1. Why? This is the number of ways of permuting n elements. If I only had one thing, a, well, then the permutation is a, right? So 1 factorial is 1. But if I had nothing, how many ways are there of arranging pink unicorns? Again, there are no pink unicorns.
Well, I certainly.
You can feel free to disagree. But let's suppose that there are no pink, fine, there are no red unicorns. Now, how many ways are there of arranging them? 1. You don't do anything. Right? That's called the gamma function in general. Right? Exactly, the empty set. You always need the empty set. And so how many combinations are there where you take nothing? 1, it's the empty set. Right? But that's combinations, not permutations. Right? With our last 15 minutes here, what I want to do is review things that we've looked at before, including, say, binary search. Now that we know how to formally analyze algorithms, we've already done this for selection sort and insertion sort. What I want to do is I want to go and revisit binary search. I want to revisit quicksort. And I want to introduce or revisit, depending on whether or not you've seen it before, merge sort. All right? So with the rest of our time today, let's go ahead and talk about binary search. The idea of it first, and then we'll codify that as an algorithm. Just as a reminder, it's sorted. It's an array that's sorted. Right? We're given this as input. We're also given a key, k. We want to search for k. Search for k. Right? The trick to binary search is exploiting the fact that it's already sorted. What we're going to do is we're going to jump right into the middle here and look at this element a sub m. Right? This is index m, right in the middle. And one of 3 things is going to happen. If a sub m is equal to the key that we're searching for, we're done. Right? We found our needle in the haystack. We can return it. Otherwise, the key is going to be less than, here. The key is going to be less than a sub m. Right? If it were less than or equal to, well, we've already taken care of that first. Right? In which case, if the key exists, where is it going to be? In the left. Search L, the left partition. Otherwise, if a sub m is less than the key, or another way of putting it, the key is larger than the middle element, then we'll search where? R, where this thing is R. Right? Now, when I present this in Computer Science 1, I usually avoid recursion because all of my labs demonstrate why you want to avoid recursion. But for today, let's go ahead and come up with some pseudocode that does use recursion. Right? So, binary search of, I'm going to take 4 things. The array A, the key K, and a left and a right index. Initially, come on, L is going to be 1, and R is going to be n, where n is the number of things in the array. And here I'm using 1 indexing, okay? Why do I give these as part of the recursion? Because ultimately what's going to happen is, if I search the left partition, I'm going to keep my L, but what happens to my R? I'm going to move it over here so that it's only this part of the array. If I search the right partition, then I'm going to move my L over here so that I'm only searching the right partition. R is unchanged. Okay? That's the idea behind passing these two things in. When you're writing recursive functions, what's the very first thing that you should do? Base case, good. L and R, they're moving in on each other. Eventually, they may be equal to each other, in which case, that's the middle element. I still need to check it. But on the next iteration or on the next recursion, what's going to happen to my fingers? They're going to go opposite of each other. If L is greater than R, then that's an empty partition. And that's when I want to stop. So if L is greater than R, I stop the recursion. And I output, what did we do with linear search when it was failed? We output the special v, right? Nothing, no null, return -1 as an index, throw an exception, no such element found, et cetera, et cetera, et cetera. Right? Otherwise, we need to do this trick over here. We'll check to see if it's equal to the thing that we're looking for. If a sub m is, or actually we need to compute m first, right? So how do I get m, oops, how do I get m given L and R? How do I get, what? Okay, I could go R minus L. That'll give me the magnitude here. That'll give me the length of this number line. Okay. That will give me the length of, oops. That'll give me the length of half the number line, but it won't actually give me this value right here. But if I start at L, okay, plus L, math, 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 that's equal to, if you want a number in the between two numbers, what is it? It's their average, right? So m is equal to L plus R over 2. This is perfectly fine for pseudocode. In fact, I would do this with pseudocode. Some considerations though. What if L and R, their sum is odd? Divide by 2. Is that a valid index? Nope. So, all right, fine. Floor it. L plus R divided by 2. You are risking, in your actual computer, you are risking overflow there. You don't do that. That's an excellent solution right there. You're not risking overflow. So, I like that solution for a practical implementation. For pseudocode, though, let's go ahead and go with this. Right. There's my M. So go ahead.
I didn't understand why you separate that.
Which one?
So you put plus L instead of the lower one.
Oh, sorry. That's my mistake. No, L. You start at L, and then you go half the distance to R. Right? So what's half the distance to R? R minus L gives you this distance. Divide by 2 gives you that distance. If you start at L, jump to M, that's M. Oh, you're risking overflow with this one right here. Because what if both your indices are very large? 2 billion and 2 billion. 2 billion plus 2 billion, that overflows an integer, right? L and R, 2 billion, that's representable, but 4 billion is not. So you end up with a negative value, divide by 2, it's just a less negative value, and now you are trying to access an index value that's negative, right? And by the way, don't feel bad for not knowing that. I think that there was a Java bug that existed for 15 years that risks this overflow in the Java standard library. It only manifests itself with extremely large arrays that you end up running out of memory before you even have this kind of index out of bounds exception, this overflow or underflow. All right? So, yeah, go ahead.
Why are you adding L and not adding 1? Oh, no.
Nope.
Wait, no.
It's just it's L in general. Not you start out at 1, but you're moving them, and so on subsequent calls to binary search, that's going to be different. So if the middle element is the thing that we're looking for, we're done. All right? Else, if a sub m is, or sorry, let's go with the key is less than a sub m, then we'll recurse on this binary search. And I'll just go ahead and shorten it to that. A, K, but now what are my updated L and R's? So if K is less than a sub m, I need to search in the L region. So what should I do with my L should be unchanged. I should move my R to be over here. Should I move it over here to be M? We already looked at M. We already looked at a sub m. So my L stays the same. My R gets updated to M minus 1, the index M minus 1. Else, if, and I'm just doing an if here to demonstrate. Of course, this is the only other condition, so it would just be a regular else. If the key is larger, then I would call binary search on A, K. R stays the same in this case. And what do I do with my L? No, not over there. M plus 1. All right? And there. That's the recursive version of binary search. Go through your 5-step process. 1, what's the input? This is one of those cases where we've got 4 inputs. Is the key relevant? No. L, R, they're not directly relevant, but the input is the thing that does change. There's only one L, there's only one R, right? So the input is going to be A. What's the size? The number of elements in the array, N. Number of elements in A. 3, what's the elementary operation? So I'm doing a lot of things here, right? First of all, base case. That's like breaking out of a loop. It's necessary to the control structure of the algorithm. Nope. An addition? A division? A floor operation? Those would all be reasonable, but they're also going to be proportional to other things like this comparison, and this comparison, right? So am I actually doing 3 comparisons? Well, first of all, this last one was, we already said that that's not necessary. Why? Because it's the only other case. If this or this, otherwise that, so you don't even need to make that 3rd comparison at all. So now we're down to 2. You could analyze it with respect to 2 comparisons, but that 2 is going to end up being a constant sitting out front, and when we go to big O analysis, who cares? Take all 3 of those things and think about it from a practical perspective. All 3 of those things get rolled up into one function call to a comparator, like you're doing in this week's lab, right? You're given a bunch of locations, and you have to implement the comparator, the compare to method, excuse me, so the comparable interface, and it doesn't matter what you compare 2 locations by, their latitude, longitude, zip code, name, whatever, right? As long as it's consistent, right? But that's only one function call. So rolling all 3 of these into one comparison is a reasonable, without loss of generality, assumption. Right? 4, how many times is the input, or how many times is the elementary operation executed with respect to the input size? We're going to have to come back to that next time. We need another tool. 5, jump to conclusions here. We already talked about it way back here since we've looked at it before. The only example that you know of a logarithmic algorithm is order, come on, it's going to be order log n. Right? So how did we get there? We'll have to discuss that next time. You need another tool called the Master Theorem. And it's not a master of anything. It's actually quite limited, but we'll do it next time.